Okay, so let's get it started. So we'll be doing week 4 today. Some questions there. So the week 4 comprises of the we move on to the convolutional neural network and fully connected neural network and use those for classification tasks mostly. Uh, so that is it. So starting off with few questions. So in CNN and fully connected neural network, so these are the two we are comparing here, and we have to match what should be the answer here. Okay. Uh, so as you know, any kind of neural network training, what to update the weights, we have to use backpropagation. Okay. So you have this parameter theta, and suppose theta ij, so that is ith the layer, and in the layer, uh, so suppose in the layer there are several nodes like this, several neurons. So jth column actually, so theta ij can be updated from the previous value, and this is the learning rate, suppose lambda, and del by uh, del the previous value. Okay, and this is the loss. Okay, loss function you have, and this is the previous value you have months. So this will be written as is coming from the subsequent ones. Okay, so x plus 1 was the subsequent layer, and like that. Okay, so this is the one. Okay, so for that you need to do gradient descent. Okay, means like backpropagation algorithm is required. Okay, so and backpropagation algorithm requires you to know the chain rule of calculus. Okay, so that will be required. Okay, uh, just to illustrate, suppose so you have this neural network, and this is the input layer. Suppose it is input layer, and you're giving the input, and this is the subsequent layer, second layer, hidden layer, and this is the final output to be used for classification tasks, let's say. And now what you have, um, these are the connection. Okay, so is it audible?
Yes, sir.
Okay, so now what we have is that, uh, so suppose we call this layer 1, this is layer 2, and layer 3. Okay, this is our numbering, and this is so you need the bias term as well. Okay, so this is the bias term as well. Okay, and okay, so this is it. Okay, now, so this output of this neuron can be written as, so first the input. Okay, so input, let's say, so it composed of, so it is layer 1. Okay, and the node is 1, numbering is 1, suppose 1. Okay, so 1 2 3 like that. Okay, and what more information do you need here? Okay, and this is the parameter. Okay, plus bias term. Suppose the bias term is taken into the uh, this. Okay, Okay, so what you end up is, so in the forward pass, so you'll have this W transpose X plus the bias term, or we can take the bias term into this one. So this is it, okay? And now this is the linear one, okay? So you have to add this sigmoid non-linearity to get the answer, okay? Now this output becomes the input for the second layer, and then you do that again to get the final output, okay? So so this is how it is, okay? Now while calculating the loss, what you have to do is that, so this is the loss function, okay? So what you do is, for suppose there are n samples, I equals to 1 to n, what you have to do is the output yi minus the output of the neural network. So that is x, this is 3, so x2, or let's not write it like that. Mm, so this is like sigma x3, let's say, okay? This difference, square difference, okay? And divided by number n. Usually 2 is also taken because this square will come out, okay? And well, if it is a, so it is a if it is a regression task, you use the square error function. If it is a classification task, use the cross entropy loss, okay? So but you've got the loss for the final layer, okay? And now you need to calculate the parameters which need to be updated according to the loss, okay? So for that, what you do is that use gradient descent algorithm, okay? And now what happens is that so for the final layer, for the final layer, you know this expression W transpose x2, okay? This is y3, okay, like that, or okay. So this is the output, okay? Or you can write it like, just to avoid confusion, you can write it like f of x2, okay? So this is our output, okay? And now what we have is that, mm, so and this W's are the weight of this connection, okay? So let's say it is 3, 2. So from 2 is moving to 3. So this is the notation, okay? Now, what you need is that for the mm, to update this parameters, okay, W32, what you have to do is you have to find, you have to suppose these are the vectors of parameters. So W32 minus lambda is learning rate, and you need the gradient, okay? So what you do is take gradient. Uh, so you need with respect to x2, right? So del x2. So how do you take this one? Okay. Uh, so okay. So this is the loss function you're taking with respect to x2, and so here it is no problem. Okay, you can take it with respect to x2 as x. It is function of x2. Okay. Acha, you can write it. Um, acha, 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 acha. This is correct. Okay, no problem. So you're taking so first so you're doing this, okay, and so this term I have written as x3, okay, here. So what you do is that you need this one, okay. So what you do, you take derivative with respect to mm, so this will be easily calculated, okay. So first with respect to x3, and then so to be precise, what I want to denote is that x3 is equals to w32 transpose x2. Okay. So this is okay. So with respect to this, and then del x3 derivative with respect to x2. Okay. So this is the chain rule that you need to use. Okay. And then you will get this one. Okay. This is the way you have to do it. Okay. And so in the gradient computation you need to use chain rule of calculus. Okay. So this one is correct. Clear? Any doubt? Okay. So little bit description on that, the better derivation, everything will find you on the videos. Okay. So this one is correct with respect to both of these. Okay. So you'll have one in both of these. Okay. So one is here. And how many? This. One here is this, and okay, you've already got the answer. So they made a very easy question actually. This is the answer. But you can check others as well. So sparse connectivity in CNN, what you do is that you don't have all these combinations, okay? All possible combinations are not there. You only have few of the combinations, okay? So so that is why it is sparse connectivity. So CNN is induces sparse connectivity, fully connected network as the name denotes. Uh, yeah, every node is connected to each other. Okay. Less number of parameters. In case of CNN, there are less number of parameters. Parameters are this W. So if you have not all the connections, then you'll have less number of parameters. Vector to vector function. So you have written it as a vector function. Okay. In both of these, CNN and FN, it will be vector to vector. Acha, in CNN, they didn't haven't written vector to vector, but it can be represented as vector. I think a little bit wrong there. The last part is correct, of course, used for classification, whether this image is a human or not, suppose face or non-face classification, those type of thing. Okay, so in convolution, what you do is that you use a filter over the image. Suppose this is the image, and now you use a filter of size, say S cross S. Okay, let's not write S here. Say it is A cross A or L cross L, something like that. A cross A, let's say. And the how many steps, so now you need to move this filter over the image. Oh, now need to move this filter over the image, and the number of steps of movement, suppose you take one step, then that is called stride. Okay, so the amount of step taken at each movement is called stride. Okay, so you move horizontally by that stride. So stride is so that one. Okay, so here you can see stride in the question. And now A cross A is the filter size. Okay, there is also some gap between these. Okay, sometimes taken, uh, which is called uh, what was that? Remember actually, just search this one. Acha, it is called padding. Okay, so what happens is that sometimes the size of the image, suppose 20 cross 20 is the size of the image, and the filter is 3 cross 3, so it is not exactly matching. Okay, so what you can do is you can pad with one zeroth layer, so all the zeros here, and this become 21 21. Okay, so now it is exactly matching with the filter. So as you can see, uh, so 7. Okay, so first it is there. Okay, next 6 movements will let it completely traverse the this horizontally. Then you can do it vertically as well. Okay, so so that is what it is. Okay, okay. So padding we've understood stride, we have understood this filter size. Okay, uh, okay. So now suppose the initial image was 20 cross 20 cross 3. So these three are what? These three are called the uh, these three are called the so in case of normal image, what you have, the three is the RGB. Okay, so the which pixels are red, which pixels are blue, and which pixels are green. That is denoted at each layer. Okay, so so it is called channel. Okay, so the three channel. So the in general we use three channel image. Okay, now what happens that so the filter has to be of the dimension 3 cross 3 cross 3 as well. You understand why? Because it has to traverse every channel of the image. Okay. Now what happens? Many times the filter is applied uh, more number of times usually. Okay. So suppose you do this. Okay. So the final result may be 20 cross 20 cross 20. So what why is it 20? It may not be 20. It may not be equal to this. Okay. So so this 20 denotes that the filter has been applied 20 times. Okay, so this is it. Okay, and so you can apply it multiple times. Okay, I mean now what happens is that so what you're doing is now pooling. So this is convolution done. Okay, now what you do that you take a filter and you want to pool it. Okay, so what does pooling means? So pooling means some sort of averaging usually. So there are average pooling, or another is so this one mean pooling. Okay, and another is max pooling. Okay, so what happens is that in mean you have to take the mean of these values. So 3 cross 3, the first one will have so you have to average 9 values. Okay, and in the max pooling you take the max of the values. Okay, and you do it for all the channels. So after the first convolution operation becomes 20 channel image. Okay, yeah, or you can say it is not image anymore, it is like 20 channel feature vector. Okay, so or feature. Okay, not a vector, of course. Vector is like one dimensional. uh, so are you able to follow, or am I too fast? Hello. Oh, channels, yes, thanks. So you're able to follow, right? Any response? Okay, yes, is able to follow. So, so you need to do pooling. Why? So the reason for the pooling is that uh, so the reason for the pooling is that you want to take the context of this filter. Say that it is 3 cross 3, so there are 9 values total in one channel. So you take the average or max of that. So you want to take some uh, what neighborhood information or like averaged out information. Okay, so why is that important? Because you take want to take the information from every single pixel and and you want to learn such that it up at at the final node it becomes one value which you can decide. Okay, so it takes importance from all the values present, okay, and compresses into a single node value. Okay, so that is why the pooling is important. It is taking importance from all the pixels, okay, inside the filter and inferring upon that. Okay, because the final task is classification, and for classification you are only going to have one value. It is above a threshold, then it is the suppose face of a human, otherwise not face of a human. So that is the classification task you have. Okay, so there are two type of pooling: average or max pooling. And as you can understand, you can there are no parameters in this. Okay, just you have to take the max of the values or you have to take the average of the values. There are no learnable parameters here. Okay, so first of thing is this number of learnable parameters is 0. Okay, next little bit mathematical definition of convolution. So suppose so this is what we call convolution. Okay, or so there is some distinction here. So let me show you actually. And one is convolution and correlation. So what happens is that you can see that convolution we do by flipping the kernel. So this filter is also called kernel. Okay, so okay, and while correlation does not flip the kernel uh, while taking this operation. Okay, so this is the difference actually. So in convolution you do flip the kernel. Okay, and so we're almost done. Okay, so another is the pooling actually reduces the size. Okay, so first what we had done, we had also induced a we have also induced a that padding. Okay, so that makes it 21. Okay, now 21 is divided, so every 3 is becoming 1 after average or max pooling. Okay, so you have to divide this 21 by 3. Okay, so the final size of the feature vector becomes 7 cross 7 cross 20. So this way you reduce the size, you keep reducing the size, so it will end up becoming 1 cross 20. Okay, okay, like that. So we do it like that. Okay, so again convolution and again pooling, like that. Okay, so this is the operations we do in a convolutional neural network, and up to finally the last node where the dimension becomes practically 1. Okay, then you can infer on it. Okay, whether whatever the classification task. Okay, so now dilation rate is same as the stride. So that is not correct. Okay, so dilation rate is actually not that important. Usually it is set at 1. That is why I did not explain. So dilation rate is, suppose you have this 3 cross 3, suppose 4 cross 4. Now the one row, column and everything of the filter does not act upon the values of the image. Okay, so so you can say that so what happens? So this is four dimensional. So suppose a row of the kernel here. Now, what I say is that you act upon this, okay? And you do the configuration with this value of the filter, also with this value, but you skip these two, okay? So then dilation is 2, okay? But stride is the moving of this filter, okay? So this is not the same. It is not important as well. Usually all of these values are taken because it gives better result. One pixel is affected in convert output by a single input pixel when even sized filters are used. Okay, so the concept is like this. When you're taking odd size filter, the benefit is that you have a center of the filter, okay, defined, okay. But in case of even sized filter, what happens that center is not defined, okay. And now what happens that suppose you're given a 2 cross 2 filter, just example, okay. So what happens if you're given a 2 cross 2 filter, then during the convolution, what happens is that uh, yeah, you're not going to get the what I mean to say is that when you are using even size filter, the acha, so this one is actually wrong actually. I mean, not one pixel is affected, every one of the pixel is affected, okay? Because this it has no exact center, okay? So suppose in pooling in the 3 cross 3, this pixel center pixel will be affected, but in this case, all of the pixel will be affected, okay? So this is the one, okay? And so derivative loss with respect to image x, okay? This is how they have written. So this is the convolution operation, and this is the correlation. Okay. So the derivative loss, while taking the derivative loss, what happens is that it is actually taking the correlation, not convolution, because it is not flipping the kernel in the reverse process. Okay. So that is why, I mean, the forward process is there, and then backward process you are taking this derivatives. Okay. And in the backward process, the derivative is, hence the kernel is not flipped. Okay. So that is why it is called correlation here. Next, this is the question we have. So Z is something, okay? So Z is some output of a convolutional, lot of convolutional layers, and now finally you're getting the Z output, okay? Now you're putting it through a ReLU function. Okay, so ReLU is this one, that function Z. So when you're putting Z into the function, what you get, this Z, if Z greater than equal to 0, 0 otherwise, okay? So now what happens is that uh, you are so you can understand that z is always greater than equals to 0, okay? And Okay, correct. Now what happens that it's sigma. Now we're putting that value fz value into this sigmoid function. So let's draw the sigmoid function as well. Okay, so this is the sigmoid function. This is z equals to, or fz. You could write fz here. Okay, fz equals to 0.5 here. Okay, and this. Oh wait. Okay, so so first thing to notice is that z. So this fz is always positive or zero. Okay, so fz is here. Okay, okay, and this is the value positive or zero. So this is the values. Okay, so what happens is 0.5 or above. So sigmoid will output 0.5, or this is the range of the sigmoid function in this case. Okay. Uh, so there is like, if it's greater than or equals to 0.5, we output as dog. So state whether the following statement true or false. Using ReLU function followed by sigmoid in the output will cause all predictions to be positive. That is correct, right? Because this is always the output, and this is the output to be classified as a dog. Okay, so it will always classify as a dog, so it will be always positive, so this is true. Correct? Understood? This is y cap here, and it's a sigmoid function. You can see this is the fz, and this is y cap, and the sigmoid function between the y cap and fz. Okay. That is what I have drawn. Clear? Clear? Any doubt? Any doubt? Clear, right? Okay. Okay, let's move on. This is the question we have. So parameter sharing. Feature data that is useful for one part of the image is probably used for another part of the image is image 2. Is one of the benefits of convolutional network along with following options. What is the true statement in convolutional network? Select all the possible answers. Okay. So what happens in that in convolutional neural network is take the case of a ordinary fully connected neural network. So what happens is that the parameters, the W's that you saw previously, are specialized for each task. Okay, and so you cannot use it for another task. Okay, but in case of this, as the number of parameters reduces, okay, so you have to, the model has to learn to not be specialized, but the parameters should be useful in several tasks. That is uh, possible. Okay, so we have to remember that in before the deep learning age, these filters were designed by people for several tasks. Okay, so each filter was for a, so each filter was different for every task. Okay, but now the parameters have to adapt so that they can be used for every possible task. Okay, that is how it is. Okay, so what happens is that now we have to answer the questions. Okay, um, okay, so let me just take a 5 minutes break. Okay, then we'll come back. Okay, and do these questions. Okay. Okay, so let's continue. Okay, so that is parameter sharing in convolutional network, which you don't have in fully connected neural network. So it is reduces the total number of parameters, okay, thus reducing overfitting. Can be used as multiple places also. Okay. So what does happen with weight sharing? Okay. So what happens that when you are using weight sharing, what it means that you are reducing the number of weights. Okay. Now what happens is that if the number of weights were more, okay, then the model has the chance to learn more things, more information with those nodes, with those weights. But now that you have removed those weight, so does not have the chance. So you have bias the model to a more simplistic design. Okay. So this simplistic design, okay. So what happens is that it's not possible for the model to learn complicated features, okay. So that is why it has increases in it increases bias, okay. Correct? Any doubt? Any doubt? Okay, so next question. So you're given a neural network F, Wij be the weight connecting neurons, AI in hidden layer 1 to Bj in hidden layer 2. Okay, okay, so this is what you've given. Now this is L is the loss function, so you need to find the gradient with respect to this weight. Okay, this is not the only weight connecting neurons AI and Bj. Okay, okay. So how do you represent that? Suppose so there are neurons AI. Okay, so what it means is that suppose you have several neurons here. Okay, so this is A1, this is A2, dot 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 somewhere that is AI. Okay, there's a bias term. Okay, so what it means is that you've already some knowledge the output is going to be. You have this bias term, bias node. Okay, and then you have several like this as well out in hidden layer 2. This is B1, B2, like that. Somewhere this BJ. So what it means is that this Z, okay, Zj is going to be summation over I, summation over, summation over. Any doubt? So this is the bias you have, okay. bj. Okay, this is bias you have for the model. Okay, this is the combination. This is the zij. If you apply sigmoid on that, then you get the final output of this node. Okay, so this is the equation we have here. Now what you need to do there, you have a loss function, loss L, and what you need to calculate is del L by del Wij. Okay, so what you can write it as del L by del Bj first of all. Okay, now now Bj is here. Okay, and now you're taking derivative with respect to Wij. Okay, now acha, acha, sorry, let me remove this one first. Okay, now so the this with respect to this Zij, it is easier to calculate. Okay, because so first, so using chain rule, first we'll do with respect to Zj. Okay, now del Zj by del Wij. Okay, now you can see the derivative with respect to this Zj and Bj is same. Why? To take so any function. So suppose you take this derivative del Zj with respect to x, suppose. Okay. Now this will be with respect to x. Okay, and this will be also with respect to x. And now wait, maybe this is not required. Okay, so you see it like this. Suppose del L by del Zj I have, or let's say by del Bj I have to see. You can write a del L by del Zj, and now del Zj by del Bj. Okay, now when you're taking derivative with respect to Bj here, so this is not dependent on Bj. Okay, so del Zj, okay, by del Bj is 1. Okay, so del L by del Bj equals to del L by del Zj. Okay, okay. Now when you're taking derivative with respect to Wij here, okay, so this becomes, so you're taking with respect to Wij, so only that AI will come. Okay, but and it is also not dependent on B, so this will go to 0. This becomes AI, and now this becomes equals to del L by del Bj. So you get the answer. This del L by del Wij is equals to del L by del Bj and Aij. AI. Okay, this one is correct. Wij is not the, so that is wrong. So that you can see, so Wij exactly represents what that weight which connects neuron AI and Bj. Okay. Hmm. No doubt, right? So first is true, second is false. Any doubt? Any doubt? So we are using chain rule as you can see for backpropagation. Okay. Next question is this one. Which of the following statement is true? The weight change criterion is a method of early stopping. So what happens in early stopping? What you do that your loss with respect to theta is falling. Okay. Now it gets to such a point that you understand this. The loss is low enough. You can stop the training. Okay. So that is called early stopping. Okay. Now they have defined a method called weight change criterion. That is a they call that it is a method of early stopping that checks whether or not the error is dropping over the epoch to decide whether to continue training or stop. So so it is not correct. Weight change criteria is not used for this. Okay. So early stopping is usually done like this. Suppose so you have theta uh, 1, this is theta 2. So take see the difference between theta 1 and theta 2 and see if it is less than suppose 10 to the minus 3 or somewhat smaller. Okay. So you take a like that. Okay. And so L2 norm tends to get more sparse weight than L1 norm. So that is wrong. Why? Because L1 is norm induces the Laplacian prior, which produces uh, sparsity. L2 is just reduces the weights little bit actually, not much. So dropout we have understood. Dropout train with probability P and test time you keep the probability 1 minus P for the weights. Okay. So in after the training the active network has a weight W, so you multiply it into 1 minus P. A single McCulloch-Pitt neuron is capable of this. Okay, so McCulloch-Pitt neuron is defined as 1, so you get 1 or 0 if this suppose your combination is greater than a threshold t and otherwise you get 0. Okay, so this is the very simple one as you can see, so that it can only handle the linear function and so this one is correct. This one is correct, linear function but not this non-linear one. So XOR is a non-linear function, right? It cannot be handled by McCulloch-Pitt neuron activation, which is simple threshold-based method, and it is linear as you can see. W transpose X it compares with a threshold. And no non-linearity, okay, no sigmoid function. So it is not possible for it to compare and produce a non-linear function. Okay, so let's go to some other questions if we can take up from here. These two I've done. Okay. Okay, maybe we can take the question number 3 here. Okay, this is what we have. The sigmoid function can be represented like this, they say. Okay. So let's write what is sigmoid function here. Sigma x is equals to 1 plus 1 upon. Is this the correct one? Yeah. This is what we call the sigmoid function. Okay. Now this is tan hyperbolic. So what is tan hyperbolic? X by 2 minus e to the power minus x by 2. For x by 2, I'm writing about e to the power x by 2 plus e to the power minus x by 2. This is tan hyperbolic x by 2. Okay. Now what you do is subtract 1 here. This becomes negative. So what happens? It becomes minus 2 times e to the power minus x by 2 divided by the numerator remains same. Okay. Now divided by 2, so this goes away. Okay. So what we are remained in minus e to the power minus x by 2 by e to the power x by 2 plus e to the power minus x by 2. Divide by this, so this goes away and this becomes minus 1 by e to the power x plus 1. It's not giving the right answer, I think. Let me just check the sigmoid form just to be sure. Okay, so we are correct there. And this is what we are getting here. This cannot be made like this. Is it correct? I have done correct. Can you check? Have I done correct here? Is the calculation correct? Maybe I should check the tan hyperbolic as well. This is tan hyperbolic as you can see. That is what we used. X by 2 because x by 2 is here. Okay. Now subtracting 1, so this becomes okay. This cancels out. This becomes the 1. Dividing by 2, so this 2 goes away. Then multiplying by ex to the power 2. So this is what we get. So they are not same. Okay. This is false. Okay. Next, the derivative of the sigmoid function is symmetric around the y-axis. You can take the derivative. Okay. Minus. Now, okay. So this becomes square first, and now taking derivative of this one. So e to the power minus x becomes plus. Okay. So is it symmetric around the y-axis? So to check symmetric around y-axis, what you have to do here? So symmetric around axis means that if you put minus x or x, it remains the same. So you replace x by minus x. This is plus, right? So replace x by minus x, it becomes e to the power x by 1 plus e to the power x square. Are these two the same? So what we have to do is multiply numerator to numerator by e to the power 2x. So what it becomes e to the power x by so this becomes e to the power x plus 1 and square. Right? So both are same. So what it means, it is symmetric around y-axis. Okay. Gradient of a sigmoid neuron vanishes at saturation. So gradient is this one, right? Or you can write this one. Are you able to see, or is it too hodgepodge? So gradient is this. So let me go to this next page actually. So gradient of sigmoid is e to the power x by 1 plus e to the power x square. Okay. Now they ask whether this vanishes at saturation. So what it means that you have to take limit x tends to infinity. Does the gradient vanish? So you have to take this limit. And if it becomes 0, then it means that the it saturates. Okay, so x or minus x for x equals to infinity as well as negative infinity. So what you have is here, as you can see, if you put infinity here, it is infinity by infinity form. Okay, so you can use the L'Hopital rule, e to the power x plus 2 comes here, 1 plus e to the power x. Okay, now if you use infinity upon infinity form again, hmm, or you can do it better way actually, too much L'Hopital. So what you do is that you divide by e to the power x, e to the power minus x plus e to the power x plus 2. Okay, now by if these two are positive by AMGM inequality, okay, so what you have is that e to the power minus x plus e to the power x is greater by 2, greater than equals to product of these of 1. Okay, AMGM equals to AM is greater than GM. Okay, this is always greater than equals to 2. Okay, okay, so this limiting case becomes 1 by 4, so it does not vanish. Okay, or am I correct? This one is wrong, as you can see. Sigmoid activation centered around 0. That's not correct. Yeah, because it is centered at 0.5. Tan hyperbolic is centered at 0. Okay. Gradient of a sigmoid neuron vanishes at saturation. Saturation means that only. The gradient does go 0. I mean, maybe I need to do it better this way. I mean, diagrammatically, you can see that. So you have this, okay. The slope does go to 0 at infinity. Okay. Okay. So what we have here again, let's see. Okay. Taking derivative, it becomes, again taking derivative, it becomes, here we are getting half. Okay. So I mean the thing was that like if you have a lesser power thing divided by more power thing, it does become 0. Not able to get here. So we have x tends to infinity, which implies you can write it like t tends to infinity substitution, t by 1 plus t square. Acha. Uh, yeah, so this is the one. So I suppose replace by another variable y here. y tends to 0, this is the 1 by t, okay? This becomes 1 by y, 1 plus 1 by y square. Multiplying by y square, what you get? Y plus 1 whole square, okay? So, acha. So now put y equals to 0 here. What you get by 0 by 1 form. So answer is 0, okay? Okay? So it at infinity it stretches to 0, okay? Clear? Any doubt? Any doubt? No doubt, right? Okay, we'll finish it up here. Okay. Thank you very much. Acha, doubt. Acha, no doubt. Okay. Any doubt? Any more doubt?
Okay.
Okay. Thank you. Hello.